Hi everyone! In today's video, we're going to start building a first-person controller for a Godot VR game. The environment you see me in here is based on the project that you build in my Getting Started in OpenXR video. As a reminder, on the side is the node tree we created in that video. All I've done is added a floor and some walls. I've also added some objects so you can see the location of my hand, the location of my head, and where the origin 3D node of our scene is. As I move around, you can see that the XR tracking system is positioning the camera and controller nodes automatically. These are all tracked in relation to the origin node. It is thus important to note that you can't control the positioning of the camera and controller nodes yourself. These are always positioned by the XR system. The origin node thus maps our physical tracking space to a location in our virtual space. We can move our origin node around the virtual space to move our player around. However, doing so correctly is something that many developers get wrong. The main mistake many developers make is thinking the origin node denotes where our player is standing. But as you can see, I can walk away from the origin point provided my room is large enough. Now if I move the origin node, I end up moving through the wall. It gets even funkier if I try and rotate the player. Whoa, that made me dizzy. Now, in my Godot 3 tutorials, we introduced a player body that follows the player around. I'm showing it doing so in slow motion here. In this tutorial, however, we'll look into a much better solution to this problem. In our node tree, I've moved our world environment, sun, floor, and walls all into a subscene just to keep things tidy. For our new approach, we're going to start by setting up a normal character body controller. We add our character body 3D node with a collision shape 3D node. We'll use default settings, but need to move the collision shape up by half its height. So we can see our player while testing, we also add a Mesh Instance 3D node with a capsule mesh. I quickly configure a transparent material for this. I also add my axes subscene here so we can visualize the orientation of our character body 3D node. If we just move our origin node out of the way, we can see our axis properly showing. Next, we're going to reparent our origin node to our character body node. In part 2, we'll create logic that moves our character body node based on controller input, and our origin node will move along with it. Basically, our character body movement logic will become similar to that of a non-XR game. However, we need to also account for physical movement of the player. We solve that by moving our character body to where our player's head is, and then move the origin in the opposite direction. All the movement code from controller input will go onto our character body node. But we're going to add a script to our origin node to handle the physical movement. Apologies that the pop-up window opened up half off screen, the joys of a widescreen monitor. We're going to give our script a class name and turn it into a tool script. This allows us to create a getConfigurations warning method to remind us that our origin node must be a child of a character body 3D node. We do this by checking the type of our parent and adding a warning to the string array this method returns. We're going to add our movement code to our physics process function. First, we obtain our character body parent and exit if we can't. We also need access to our camera node, which we know will be a child of the origin node. So let's first add a check to our configuration warnings, and then retrieve the camera node in our physics process. To start our logic, we want to obtain the transform of a camera in the local space of our character body node. We do this by multiplying the transform of our origin node with the transform of our camera. Now we're going to determine our new position by taking our camera position and removing the height. We can easily do this by multiplying a vector with the y component set to 0. Next, we transform this position into world space by multiplying with our character body's global transform. Now we can move our character body using Move and Collide. Next, we need to calculate how much we actually moved, as we may have collided with an object. We need to convert that movement back into the character body's local space, and then apply the inverse movement to our origin node. Now we can see that as I'm walking around, our character body follows me. The origin node being moved back results in it returning to its original position. Now that our character body moves to the correct location, we also want its orientation to match the player's. For this, we take the camera transform we already obtained and remove both the position and tilt from this transform. We start by calculating our forward vector. We can obtain this by taking the z component of our transform's bases. We zero out the y component with our multiplication trick. Next, we zero out the origin of our transform to remove position info. And we use our looking at function with our forward vector to remove our tilt. As we're working in the local space of our character body, we can simply use the up vector. Now we apply the rotation to our character body. We only apply this to our bases because we do not want to rotate the position of the character body. And then we apply the inverse of our rotation to our origin. One last thing we forgot. Since this is a tool script, we need to make sure our physics logic only runs when we're not in the editor. Back in our scene, we're quickly going to add an obstacle to test our collision logic. I don't have enough space in my room to walk into the walls. I've added a static body 3D node with a collision shape node and a mesh instance node to create a simple box. Now we can see as we walk around that our character body orients itself with the player. We can also see that when we try to walk through the obstacle, our player body stays behind. We do, however, want to prevent the player from just walking on, so we'll add some basic fade to black logic next. In order to know whether we want to fade to black, we can compare the location we calculated that our character body should be at with where it actually is. So we calculate this as the distance between our global transform and our new position. I'm forgetting to prefix this with our character body. We will correct that in a moment. We'll define two export variables to control this. The first defines how far away we need to be before we start our fade. The second is the distance until we fully fade to black. Now we can calculate our fade by subtracting our max distance from our calculated distance, dividing it by our fade distance, and then clamping it between 0 and 1. Before we continue, we first need to implement our fade itself. We start by adding a Node 3D node to our camera node, and we save that as a new scene. Next, we add a script to that node. Here we add a new export variable to control our fade. Next, we add a Mesh Instance 3D node and create a plane mesh for this. The default size of 2 by 2 meters is perfect, but we do want this Z-aligned. We create a shader material for this and create a new shader. We start by implementing a vertex shader that uses our vertex data directly and simply sets the Z and W component to 1. We now have a full screen rectangle. We also need to set our render mode, so we ignore our depth, we skip our vertex transform logic, we make this unshaded, and we disable culling. Now we add a uniform that controls our alpha value. And we implement our fragment shader so the albedo becomes black and our alpha is set to our uniform. We're also going to set the render priority to 90, so we ensure this material is rendered last. Back in our script, we're going to add a setter function to our fade variable. It simply assigns the value, and if we're inside our tree, we call an update function. We're also going to call this update function from our ready function. We don't need our process function, so I'll remove that. In our update fade function, we check if our fade is 0. If so, we hide our mesh. We don't want to render a full screen, fully transparent quad. If we do have a fade, we do show our mesh, and we set our alpha value on our material. Now we also make this a tool script so we can see it working in our editor. As you can see, it works. To complete the fade script, we also give it a class name. This allows us to create an export variable on our origin node script to hook up our fade effect. Then if set, we assign our fade value. Back in our scene, we can assign our fade effect to our fade effect node. This way, we don't need to assume where this node is located. Finally, we can add in the character body prefix when calculating our distance. We also correct the settings as I change them around a bit. And as we can see, it all works. That's all we have time for today. In the next video, we're going to add controller-based movement. And after that, we'll look into implementing a recenter feature and height calibration. Thanks to all my patrons and YouTube members for sticking by me for so long. It's been a full-on year for me so far. See you next time!